This is Dr. Furushani, and in this video, I'm going to show you how to run a multiple linear regression analysis using JASP. Imagine that we have two independent variables and one dependent variable. So I call my independent variables as IV1 and IV2, that I can call them also as predictors in the context of regression analysis. And also I call my dependent variable as DV, that I can also name it as outcome variable. And so imagine I have a hypothesis or maybe a research question, assuming that my independent variables can significantly predict my dependent variable. I also want to see what is the direction of prediction. I want to see if, for example, higher levels of my independent variables can predict higher levels of dependent variables, or higher levels of my independent variables can predict lower levels of my dependent variable. So for such hypothesis or research questions, multiple linear regression can be a good analysis. And also, if you had only one IV, one independent variable, you still could run the same type of analysis, but just you could ignore some specific assumption checks or statistics for that. So for running the multiple linear regression in JASP, you use the regression icon. And sometimes also some types of analysis, if you can't find it in default version of the JASP, you can use the plus option and we can add that type of analysis. But linear regression analysis is usually included in the original versions of recent versions of JASP. So I click on regression, then I click on linear regression, because this is the type of analysis that I'm looking for. And so you can see that this first box is clear, like dependent variable. That means that your dependent or outcome variable can go here. However, JASP is using some unusual terms for predictors that, for example, use the term covariates. That does not necessarily means that you have to only include covariates in this box. You actually can include your independent variables or your predictors also in the box of covariates. So remember that covariates in this part of JASP actually means independent variables or predictors that you can include that. So when you include that, you can automatically get most of your main results here, but not assumption checks that you need. So it's a good point for linear regression analysis that you can run the assumption checks and main analysis at the same time. However, it needs you to tick a few boxes in the setting. So now I need to tick some more settings to make sure that I have a comprehensive view of my outputs and also main results, and also a comprehensive check of my assumptions. So the first thing is Dubin-Watson here that I need to tick, that is that can help to check the assumption of independence that I will explain in this interpretation shortly. The next one is confidence interval, that usually if you are writing a report based on APA format, you need to usually report confidence interval. So that's also important to tick. The next one is tolerance and VIF that can help you to check the assumption of multicollinearity that I will explain its interpretation shortly. But for now, you make sure that you tick these options. And if you want to also have your descriptive statistics here, instead of checking that separately in the descriptive, you can also tick it here, and it can give you some basic descriptive statistics for each variable as well. And the next part is case-wise diagnostics that can help you to detect influential outliers. Remember that if you, for example, tick here, it can show you the outliers that are 3 standard deviation above or below the average scores. However, I would recommend ticking Cook's distance because this statistic can show you the influential outliers because not all outliers are necessarily problematic for regression model. But Cook's distance value can tell you if a certain outlier can negatively impact your regression model, and you may need to consider removing that outlier from your data. So that's why I would suggest ticking this option here, and I will explain how to interpret that shortly. You don't need to change anything in method specification, but in the plots, you need also to, in residual plots, tick residuals versus predicted that can help you to check two assumptions of linearity and homoscedasticity that I will explain its interpretation shortly. And the last thing you need to tick is QQ plot of standardized residuals that can actually help you to check the assumption of normality of residuals that I will explain its interpretation in the output as well. So now everything is ready. We just make sure that you ticked all of these options here. And if you have ticked all of these, you can make sure that you're all good to have a comprehensive output. So, but before interpreting the main results of your regression model, I strongly recommend to first check the parts of your output that are relevant to your assumptions. Because if there is a very significant violation of your assumptions, uh, your main results of regression analysis are not valid to report. So that's why it's always best to check your assumptions first and then go to check and report the results of your regression analysis. If you have a violation, a significant violation with multiple assumptions, then you need to consider some measures to deal with violation that I will explain these measures in another video. So the first part about assumption checks that you can check is Durbin-Watson value. For Durbin-Watson value, what you are interested to check is this statistic, this column, and specifically for model 1, because if you see here, we only have your variables in model 1, not model 0. So that's why you need to check all the statistics for model 1. So this column is statistic and model 1. So as long as this statistic, the statistic of Durbin-Watson for your regression model, is around the value of 2, that means that this assumption is met. That means that the assumption of independence is met. And just remember that this is one of the measures to check the assumption of independence. There are other non-statistical way also to check the assumption of independence that you can see in all statistical textbook. However, for a statistical checking of the assumption of independence, you can check this value, and as long as it's close to the value of 2, that means that this assumption is met. Like for example, here, you can see that it's very close to the value of 2 so that we can say that it is met. For example, if it was 1.9, still you could consider that because it was close to 2. So that's all you need to check for this table. The next statistic that you need to check is from this table, the table of coefficient, and the statistic of VIF or tolerance. I would recommend checking VIF because it's a more lenient measure, and usually you have easier job to interpret and check this assumption with VIF. How to interpret that? As long as the values for VIF in this column are less than 10, you can say that the assumption of multicollinearity is met, or there is no concern with multicollinearity. Multicollinearity means that your independent variables or your predictors, like for example your IV and IV1 and IV2 are not highly correlated, because if they are highly correlated, that may show that they are just one variable, not two variable. So that's why. So as long as it's less than 10, you can say that there is no concern with multicollinearity and this assumption is met. And the next assumption that you need to check is coexistence. So ideally, you expect that your coexistence, this table about influential outliers is empty. So that means that there is no participant that has any coexistence above the value of 1. So you remember that in our setting, the coexistence by default was set to be above 1. That is the global conventions for coexistence, that if all participants have a coexistence less than 1, you don't see anything in this table. And that is a good sign. That means that you have no participant that can be considered as influential outlier. And it suggests that you don't need to remove any participants from your uh, data set because of being an outlier. Even though the descriptive statistics of outliers show that you have outliers, you still don't have to remove them as long as this table here is empty. So we can say that the assumption of not having influential outlier also is met. And the last parts that you can check for your assumption checks is these two plots. So this first plot, a scatter plot of predicted values versus residuals, it is actually to check two assumptions. The first assumption can be linearity. Linearity can be met. We can see that our assumption of linearity is met if you don't see any particular shape or pattern in the data points here. More specifically, we don't want to see a U shape. We don't want to see that this data points is shaping a U shape or a converted U shape. Like for example, what you can see, I'm showing that, and you cannot see a shape like U in this plot. So that means that there is probably no concern with the violation of the assumption of linearity. That means that both of our predictor variables can have a linear relationship with our dependent variable. However, please note that this is the most lenient way to check the assumption of linearity. There are some stricter ways also to check the assumption of linearity. Like for example, we are checking the scatter plot of like bivariate correlation, that I will explain those ways in the tutorial about bivariate correlation. But for now, as long as you don't see a U-shape, you can say that the assumption of linearity is met. The other assumption that you can check based on the same plot is the assumption of homoscedasticity. So you can say that the assumption of homoscedasticity is met if two conditions are presented in this plot. The first condition is that if the data points above and below these lines are evenly distributed, like for example, you can see that there are almost the same amount of data above and below this line. And also you can see almost a symmetric pattern in distribution of data. You can say that either, like for example, the left side and right side, or either the above and below the line are almost symmetric. I don't say that a very perfectly symmetric pattern, but almost are symmetric. And also the data points are distributed all around the plot. So they are all good signs based on which you can say that the assumption of homoscedasticity is met. And also the other point is that you shouldn't see a cone shape in the data point. The data point should not shape a cone shape or triangle shape in the data. And you cannot see that. For example, if you see my mouse, so we can see that these data are not shaping a cone shape either this way or the other way. On the left side or right side, you don't see any cone shape in the data. So these are all good signs to conclude that the assumption of homoscedasticity is also met based on this plot. And the last assumption is the assumption of normality of residuals. And remember that it is about normality of residuals, not normality of raw data. Normality of raw data or normal distribution is not an assumption for regression analysis. What you are interested in is the normality of residuals for your whole mediation model, not for individual variables. So, but it has a similar interpretation to normality of raw data. So as long as you see that your data points are presented around these lines, we can say that you have this assumption is met. However, here you can see that some of the data points are a little bit far from the line that you can see in this plot. So in that way, you can conclude that maybe there are some slight violation from normality. So normality of residuals is not perfectly met based on what you can see in this plot. If it was perfectly met, you could see all the lines, like for example, this part of the line, you could see that all the data were like this, like almost sticking to this line. But it's not the case here. So that means that we potentially could do some additional steps to fix this assumption violation that I will explain these steps in another tutorial video. But imagine that for now we can ignore this and we can say that our assumptions are okay and we can interpret our results. So the first thing that you need to report or consider for your regression model is this table, and especially model 1, because all of your variables are in model 1. So what is important to report in this model is R2 or R squared statistic. R squared statistic can explain that how much these two independent variables together can predict the variance of your or variations in your dependent variables. So for example, our R squared here is 0.17. That means that these two variables together can explain 17% of variance of our dependent variable. So this is the interpretation for R squared. However, we still cannot say whether we still cannot confidently have this interpretation because we don't know whether this statistic is significant or is not significant. How we can check is significant? The significance of R squared or your general model can be checked through ANOVA, like through the next table. So the p-value here is not relevant to your R squared. This p-value here actually is relevant to your R squared. So as long as the if a statistic from your ANOVA test is significant, like less than 0.05, you can say that your R squared, your interpretation for R squared is valid. So now, because this is significant, because the ANOVA is significant, we can say that our interpretation that 17% of that these two variables together can explain 17% of variance of this variable. This is a valid interpretation because it's significant. The next part that, however, so we now know that our predictors together can significantly predict our outcome variable, but we don't know how they individually can predict our outcome variable. We also don't know based on this statistic what is the direction of prediction. We don't know whether higher levels of these predictors can predict higher levels of DV or higher levels of these predictors can predict lower levels of DV. So this is why we need to check this table, that is coefficient, that you can see the statistics are presented separately for each predictors, that for IV1 and IV2. So here you need to report on a standardized coefficient that usually is reported with the symbol of B, and you can report a standardized coefficient that usually reported with the symbol of beta. And here you can see significance for each coefficient. So for example, here you can see for our first independent variables, the direction of coefficient is negative. That means that higher levels of this variable, like IB1, is associated with lower levels of our dependent variable. So that is an inverse effect, or that is actually a negative prediction. However, the second predictor has a positive coefficient that you can see that this is positive. That means that higher levels of our second predictor is associated with higher levels of uh, our dependent variables. So they are predicting our dependent variables in opposite ways. So that is what we couldn't see in this table, what we can see here. Another important information that we can get from this table is that they have both significant contribution to the prediction. So here we could see that they together have a significant predictive effect. But here we can see that even if we consider them individually, each of them can have a significant effect. So the significance of uh, prediction for each independent variable is checked through the significance of t value, like the p-value for the t statistic for that specific independent variable. So you can see that here the p-value is less than 0.05 for both of our variables, independent variables. That means that both of these predictions are significant. And you also may want to interpret the magnitude of the significance, like for example, saying that it's a large effect or is a small effect. And we can interpret that actually based on the standardized effects. That's why standardized and unstandardized effects have the same significance interpretation. But the reason that we report standardized effects in addition to unstandardized one is that we can interpret effect size based on standardized effects. Uh, for example, the effect size, if our standardized effects is less than 30, less than 0.30, we can say that it's a small effect. For example, here we have almost, it's close to 0.30, but it's still not above 0.30. So we can say it's a small effects for both of the predictions, or a small to medium effects. We can say that based on Cohen's guidelines. But it's not actually a very important or necessary part to interpret. Just refer to that just in case. And you can also, of course, you can also mention the confidence intervals in your statistical report, but that's all you need to report. And finally, you can also see descriptive for each variable that you could also check that through the descriptive functions as well. So that's all you need to report in terms of assumption checks and in terms of main analyses when you run multiple linear regression analysis. Finally, if you'd like support with writing up the results and interpretation for multiple linear regression in your research paper, thesis, or assignments, feel free to book a proofreading session using the link provided in the channel description.